Next section is derivation of the Reynolds transport theorem. Okay, we consider one dimensional of flow through a fixed control volume. In red, in the green lines, this one is a fixed control volume represented by green lines, and the orange line is the system boundary as time t plus del t. Okay, so at time t, we can say that the B system, the property B system and B control volume is the same. Okay, at time t3 plus t plus delta t, you can see that the system is moved to the in the red color. Okay, so B system is equal to the B control volume subtract B1, this one is B1, and plus B2, this is B2. Okay, and we can write that B1 B2 is equal to rho 2 B2 A2 V2 and del T. So that is come from, if we focus on this B2, the quantity of the fluid property is equal to B2 times M2. Okay, from M2 is equal to the density times the volume 2. Okay, and this equal to, for B2 low 2, and for volume we can use the Q2 times D2 dt2. Okay, that is the from volume is equal because the discharge is equal to volume per unit time, so we can substitute volume in terms of discharge Q and dt, and for Q we can convert to Q equal to V2 velocity times area and d2 dt. Okay, that is the how to get this equation, b2 rho b2 v2 a2 v2 and time dt. Okay, and we can prove that the rate of change of the B system is equal to rate of change of the fluid property in the control volume plus the rate of change at outward. Okay, subtract the rate of change itself inward. Okay, b out and b in. Okay, so inflow rate, okay, may be not equal to outflow rate. Okay, b out. Therefore, the property of the b for the control volume is not the same as the system. And if we focus on the outflow volume, look at this, is outflow volume is if their volume is equal to del L. Okay, this if we have the length L and time dA del A. And for del B is equal to B times M is equal to B times flow del A and equal to substitute del A in this equation. So D rho the small r length times dA. Okay, and finally we got the del B is equal to B rho times V times dt and A and dA. Okay, for the second equation. And in case of velocity is not not perpendicular to the control surface. Okay, in this case the n is the unit vector, outflow unit normal unit vector, and if v is not perpendicular to the surface, okay, this is surface. Okay, so from equation 2, so del B is equal to this equation. Okay, and we convert to for the del B outflow in terms of limit, and this can write the outflow rate of B, okay, in terms of integration. Okay, and you can see that is a v cos theta. This is v cos theta. So definition of, we can convert from v cos theta to the dot product. Definition of dot product, v cos theta equal to v dot n. Okay, so in this case, if we look at the surface, if the velocity v is an angle of theta between the unit vector n that is on theta, so this theta is greater than 90 degree. It looks like this. It occurs on the inflow surface, and for outflow surface the theta is less than 90. Okay, less than 90. The angle between the unit vector and velocity, and velocity. In case of the inflow, we can do the same for the flow rate of the B in. Based on this equation, the integration along the control surface at the inflow equal to rho, integration of rho B v dot n and dA. And we find the difference between B flow rate of out and in. Okay, so we got this equation, and we substitute in the first equation. So we got the differentials of the B system respect to time is equal to the rate of change of B in the control volume plus the rate of change at the surface. Okay. And this more clear, and this for make it for the inflow, we expect that the theta is greater than 90 degree for inflow, and this show that in case of the move in, you can see they expect that theta is greater than 90, and move out the theta is less than 90 in terms of the angle. Okay, so we can got this equation for the Reynolds transport theorem. General form of Reynolds transport theorem for fixed non-deformed control volume. The first term is we call rate of change of fluid. A fluid property with the time equal to rate change of the fluid property inside the control volume plus the net flow rate of fluid across the control surface. Okay.